Okay, so today we begin uh, a series of lectures on the special theory of relativity, and so I'll start. The first two lectures would be a prelude, actually, and I would like to say that you could have discovered the special theory of relativity in high school, of course, assuming that you are infinitely smart, etc., etc. Okay, so let's get started. Okay, so just before we do that, let us recall some things about electromagnetism. Okay, so one interesting fact is that that the magnetic, the force on a charged particle due to a magnetic field is I would say conservative in the sense that energy is conserved. Okay, even though the force is velocity dependent. We know other velocity dependent forces like friction, but they are not conservative. Right, so we have this force, right? If Q is the charge and V is the velocity. This is the force, and the reason it's this is the force, and you can see that F dot V is 0, and there's something called work energy theorem which tells you that this would be the work done. Okay, and that will give you the change in energy. So if you don't remember also, it's okay, you look up work energy theory in mechanics. Or you can prove it from first principles, because F dot ds is work done, and ds by dt is velocity. Okay. So this is trivial because v cross v is perpendicular, always perpendicular to v, so F dot v is always 0. Okay, so this is something very, very unusual force. Okay, so this makes it, and then Maxwell's equations. Okay, show that electric and that it. I don't want to say that show that it couples the electric field and the magnetic field. Okay, so things we know, for instance, is, for example, changing or time varying. Okay, electric field can create a magnetic field, and vice versa. We know this, right? This doesn't require Maxwell's equations, and that's why. So Maxwell unified electricity and magnetism, and so that's why we call it electromagnetism today. We don't call it electricity and magnetism. And eventually, electromagnetism gets unified something called with weak. So in particle physics, you say electroweak. Okay, magnetism is dropped, the word. Okay, so these are some simple facts. I guess you people know this, right?
Yes, sir.
Okay, but these are useful, and so this makes electromagnetism special. It is special and different. Okay, and we will see how. We will see. So so I just want to do some background. Okay, I just want to write Maxwell's equations in SI units. So I write it in the following. Okay, in free space with sources. Okay, so this is what. Okay, so this is arbitrary uh, time dependent Maxwell's equations. And but of course, I mean, I claimed you could do things in high school, but I'm going to assume a little bit more than that. But actually, you will see later that for all the arguments that I would use, other than some properties which are easier to see in this form, um, we will use things which we knew in high school, like Biot-Savart's law, Ampere's law, things, Coulomb's law, these kind of things. We knew them as bunch of laws, okay, but which get unified by this beautiful set of equations. Okay, so is there anybody in this class who has never seen these equations in this form? Okay.
Sir, I have a different question.
Hmm.
Uh, what is the role played by the SI unit that you have told that you are going to write the equations in SI unit?
Okay. So, I mean, it depends on, I mean, there are other units. We will switch to a different set of units. And so what we will see is that electric fields and magnetic fields, mix. And but dimensionally in SI units, electric fields and magnetic fields are measured in different units. Okay, so we would like to work in so this is standard what is done in BSc or first year physics at IIT. So this
So,
is
sir, by saying different units, do you mean like SI and CGS are different
yeah,
units, or do you
exactly.
mean?
That's all I mean. CGS,
Um,
Gaussian. We'll move to something called Gaussian units soon.
yes.
Okay, that's all I mean. Nothing deep. Okay, so I want to write something in familiar form. Okay, so okay, good. So there are many features out here, but first I wanted to point out some things here. Okay, so so there are two terms which I will circle here. These are sources, right? Okay, rho is charge density, and J is current density. And I'm sure you are used to putting dB by dt on the right hand side, etc. The reason I want to write it out this way is that, and there are no sources here. Okay, there's nothing out here. So for me, these are differential equations where if you give me rho and j, and some, of course, some probably fall off boundary conditions infinity, I can solve these equations for E and B. Okay, they are coupled. Okay, so let's do some counting, and we'll do the counting first by counting. This is a scalar equation, so it is 1. The counting with this will be 1. Del dot B equal to 0 is also 1. But del cross E is a vector equation, so there are 3 equations, 1 for each direction. Again, you get 3 from del cross B. So there are 8 equations. For 6 unknowns. Do you see that? Because E and B are, I'm counting each vector as 3 degrees of freedom in some sense, field degree of freedom in some sense. So we have 3 from E and 3 from B, right? So 6 unknowns and 8 equations. Is this counting clear? What I've done? Okay. So usually if you're algebraic equations, we would want 6 equations and 6 unknowns, right? I mean, something like that only. Like that. So it appears to be overdetermined. Okay, so actually what you can show is that these two equations, 3 plus 3, 6, actually in some sense determine the first two equations, del dot E and del dot B. And so, okay, so equations involving del dot E and del dot B follow from the equations involving del cross E and del cross B, provided we assume that the sources satisfy a consistency condition Usually I should write it the other way, but okay. First d rho by dt, but I wrote it this way. Doesn't matter. Okay, so this is what is this called? This is equation?
Continuity equation.
Exactly. Okay, so it's a consistency condition. Okay, so I will ask you to check this. So what you do is I'll only give the hint. Take the divergence of both the curl equations. Okay, and you should see up to some additive thing you should get these two equations. Okay, so you can just check that. So this is it. Okay, so check this. A simple thing. Okay, so this is just in terms of counting degrees of freedom. Then there are some more features which are interesting. Okay, so we can, if you go back to these equations, and we'll find that we already did this earlier, that E, J are polar vectors. Okay, rho is a scalar, not pseudoscalar, under rotations. Okay, B, what is B? It's an axial vector. Okay, you remember early on in this course we decided how things transform under parity also, right? And rotations. Okay, so this part is parity. Okay, so B changes sign, rather B doesn't change sign under parity. Okay, so are these points clear? So you can go back. A simple way to do is to go and check, take this equation for instance, and you look at it and you see that del cross E is a polar vector, del cross that, this will become an axial vector. So the only consistent way is dB by dt is axial, which follows if B is axial, so on and so forth. You can check consistently that it goes through. Okay. Is this point clear? So this is one property. Another one is equations are linear. Okay, so let's just call these equations, all these four equations, we'll just call them ME, short for Maxwell's equations. Okay, so suppose, so let me explain this. Suppose suppose E1 and B1 are solutions to ME with sources rho 1, J1. Okay. Similarly, so I'm hiding the space-time arguments. E2, B2, be solutions for sources to ME with sources rho 2. Okay. Is this clear? So we have E1, so you put two sources, put a bunch of sources, rho 1, J1, and ask what you solve the equations, and then you get E1, B1 as you're solving. Okay. It might be very, very hard, but that is not important. Suppose we can solve it, that's what we get. Similarly, if you change the sources to rho 2 at J2, okay, so then okay, alpha E1 plus beta E2, alpha B1 plus beta B2 are solutions to ME with sources. What are the sources? Anybody?
Plus rho 2 and
Alpha rho 1 plus beta rho 2 and alpha J1 plus beta J. Okay, so these are obvious properties of these equations, and you can see, I mean, E, B, everything occur only linearly in this thing. There's no B square coming, no E square or some BE, some kind of term or rho J. All come with only one. If you associate degree 1 with E, rho, J, B, every equation is degree 1. And no homogeneous pieces beyond that. Is this point clear? Okay, so these are all standard properties. Okay. This is also true in your high school level thing, in the sense that even if you look at Biot-Savart's law or whatever, you put the sources. Okay, so those are usually there for, quasi-static situations or something like that. But doesn't matter within that regime of validity. Okay, so that linearity you can see even at high school level. But it's much more cleaner to look at it from directly from Maxwell's equations. Okay, so this is the background. And so earlier in this course, we studied the Galilean group, studied and obtained actually the Galilean group as symmetries of which equations? Of Newton's equations of motion in mechanics, right? So we just looked at something like F equal to ma, right? That's what we did. Okay, and this group, this not this group consists of what are all the ingredients? There were translations in space and time, right? So these are 4 parameters. Rotations. How many parameters with rotations? Spatial rotations. Somebody? How many parameters?
3.
Just 3.
Just 3. Okay. And then Galilean boosts, right? How many parameters?
3.
3 again. Okay. So what we will do is we will ask a similar question of Maxwell's equations, and then we will ask. We would like to ask, will we recover something like this? Okay. And so what we will see is that these work with ME. So this means works ME is okay. ME agrees with this, but ME does not agree with Galilean law. Okay. So what we will find is that we will see that this has to be replaced by something else called Lorentz boost. Okay, so this follows from studying Maxwell's equations and its invariances. Okay, so what happens is that there is a conflict. This implies that there is a conflict between the Newton's equations in mechanics and everything. Okay, so a priori, one of them needs to be modified. Okay, why should I? Why am I saying that there is a conflict? Any idea? So just go back. Let's think about how we got the Galilean group. We asked that two observers mutually. We defined something called two mutually inertial observers. They should agree on forces. That was what we had in mind. Okay, and we're going to be doing the same thing even here. Okay, even with Maxwell's equations. So what it says that if you have charged particles, you get one invariance. If you have uncharged particles, you get something else. That doesn't make sense. Okay, so that is the conflict. Okay, and one of them has to be modified. And theoretically, you cannot say which one should be corrected, but we will see. We will see that Newton's equations need some kind of correction. Okay, that is something. And the intuition that one has is a special relativity. So, folklore, SR is important, is seen only when we are dealing with velocities that are comparable to the speed of light, right? Do you agree with this statement?
So the effects that come out of special relativity uh, may seem important only when the velocities are high, but special relativity provides us the proper transformation for electricity
But I mean, no, the thing is,
electromagnetism at any velocity.
so the point here is that we would like to, so if velocities are small, so if say u is some velocity and its magnitude is u, if u by c is much, much less than 1, okay, we can neglect, right? We can neglect. That is the point, right? This is what I'm trying to say. This is what we think. Do you agree? I mean, this is what I'm saying.
Sir, would could we say magnetism occurs like even at low velocity?
Exactly.
So
Yeah.
special relativity
Yeah,
is allowed.
exactly. Yeah. So this is the point. But we'll quantify this. Okay. Yeah. So the point is, this is not true for EM. Wow. Okay. And we will derive this. We will see. Okay. So for the rest of the lecture, we will focus only on situations where u by c is much, much less than 1. Okay. And so the point would be, is there some way in which we could, so we will do this, and we will see, we will study the effects, okay, at the leading power of, and we will see. And as somebody just pointed out, magnetism, and which I also mentioned earlier, is that the forces are velocity dependent. And one thing we do know, so the point here is that force, that law has been tested in the lab. That Q V cross B has been tested in this thing, at least at low velocities. Yeah, fine. Okay, so that's all we will need. Okay, so let us go back and now study, in some sense, invariances of ME, but at a very low bro level. Okay, at a very simple level. Okay, so let us go ahead and okay, good. Okay, so what I have, these boxes represent two observers, and we already discussed these observers A and B. Okay, and so the frame means just choosing some coordinates. So A has coordinates x and t, and x prime and t prime. Okay, and so we are going to assume, let A and B be mutually inertial. We have defined this, right? What does that mean? What does that mean?
Related by a Gaussian transformation.
No.
There is no related acceleration.
So they will agree on forces. Let's use that definition. Okay. And then consequence we derived. Then we looked at Maxwell. We looked at Newton's equations and derived Galileo. Okay, so here so the basic definition is not that, right? Basic definition is they will so basic thing is observers A and B will agree on forces. In particular, if observer A sees no force on a particle, what will observer B say?
You'll also say the same.
Will also say the same thing. Okay, so we are going to take even more simpler situations. So there is not even forces. We would worry about units, something. We will do all those things. Even more simpler. Okay, so this is what we will do. Okay, and now I'll just say that let B be moving with constant velocity u with respect to let observer B be moving constant velocity u in the frame of observer A. Okay, so this is just a consequence of consequence of Newton's first law actually, because we are not looking at situation. Okay, is this clear? Okay, so this is what is going on, and so this is what I will assume, and now we will do a thought experiment. Okay, and the experiment, I'll set it up now. It's as follows. Observer A has two masses lying at rest in her frame. Okay, one mass has no electric charge, has no charge, it's not electrically charged, and the other has charge Q. Okay, so this is so what does that mean? So now one of them only one of the reason to take two masses rather than one is that I want to have a situation where one particle will not feel, one mass will not feel the electromagnetic field because it's chargeless, the other will. Okay, so this just to contrast what will happen. Okay, further, okay, this is one thing. Let A measures a magnetic field of xt in the region Okay, further, there is no electric field. Okay, so now question to you is, what are the forces on the two masses? Are there any forces? There are no other forces other than what I'm saying. Okay, so there, see that the magnetic field will not act on the mass, second mass, even though it's charged. Why?
Zero velocity.
Exactly. Right. Okay. So now we are now in the situation which I just mentioned, that both masses experience no force and remain at rest. Simple, right? Okay. So now let us view the same thing from the viewpoint of observer B. Okay. First thing is, what can we say about the two masses? The two masses, will they be at rest?
They will be moving with a constant velocity.
Yeah. And what is the constant velocity?
The velocity of the frame B.
No, minus of that, right? This is clear? Minus u. Because they rest in frame A and B is moving with respect to u. So if you have to make u come to rest, you have to subtract minus u. Is this point clear? It's minus u. Okay.
Yes.
Okay. Very
Yes.
good. Okay. And the thing is that, okay, that's good. So observer B should also see no force. Right? That's what we want. But so let's do but naively. The charged particle will experience a force which would be minus u cross B into Q. Is this clear? Okay. So this is what you would have said, and but this cannot be correct. No, this cannot be correct. But of course, the particle which has no charge, there will be no force on it. So yeah. So if you just believe this, then what is happening is that according to observer B, there's a force acting on the charged particle and it should start accelerating and move off. But of course, an observer A seeing them just both lying dead on the table and not doing anything, these two don't agree, right? So obviously this cannot be correct. Is this point clear? This is very, very naive, but this can't be correct. Do you agree?
Yes, sir.
Yes.
Okay. Okay. So there must be a new force, an additional force, okay, that should cancel this. That first thing is should act only on charged particles. Right? It should not act on chargeless particles, right? Because then that force will make that other, now the charge which we had no problem with will have problems, right? Okay. Only on charged particles and cancel this. Okay. So now we will be slightly more sophisticated than just saying that. So let's so to do this, let us focus on the electromagnetic fields. Okay, so for A, what we have done, we said there is no, this much we know. Okay. What about observer B? Okay, so I don't know the answer to this, so let's just do this. E prime, and it will be measured in some electric field, some magnetic field. This is a general form. I'm not saying anything. Okay, so the question is, what should this? Okay, so the reason I'm writing this is because I want something which will act only on charged particles, and as far as we know, only electric and magnetic fields can do that. So let's hope that something like this can happen. Okay, so is this clear? This is just, I'm not saying anything about E prime and B prime. So, and we will work out. Okay, so suppose observer B let me not do this first. Let me erase this. So the electromagnetic force Q into, this is the electric force, plus minus U cross B prime. Do you agree with this? Because it's moving with minus U. So it's a little better than this, right? So here I didn't even distinguish between B and B prime. I'm just saying, let's just go ahead and do this. Okay, and this question mark should be 0. Right? This is what we want. This is much weaker than what I wrote here. Here was something wrong. That was non-zero, clearly. But at least here this works. So now, can we figure out E prime and B prime? Okay, just using this data, and the answer is yes. And so I'll need, so what we will do is that let assume that E prime should be writable as some function of U, E. In general, if there were electric fields also non-zero, E and B and B prime should also be some function of E and B. We should be able to write it. Okay. Further, of course, I want to say this is 0 in our example now. E is 0 for us. Is this point clear? That there has to be some function. They have to be related. It can't be that electric field in one frame doesn't, electromagnetic fields in one frame don't. So this is all I'm saying. So question is, what is, what is the, so the question here is what is the most general form? For these things. Okay, so before we do that, we'll write some properties. By the way, you can interrupt me anytime because I might be going fast. Some properties here are following. So what happens if I put u equal to 0 in this? So I'm not going to set e equal to 0. I'll just write something. So e prime of 0 e b. What should this be equal to?
E.
E itself. Right? Nothing deep. They're in the same frame. There's no. Okay. We are also assume that they align their axis, so no rotations, nothing is going on. Right? Similarly, b prime of 0, e and b should be b. Right? Same thing. So this is first property. Second property is linearity of Maxwell's equations. Okay, so suppose what implies the following. So suppose we have E1, B1, and E2, B2 in frame A. So two situations where there's electric field 1 and the battery field B1 and this thing. So we have like we did in superposition thing. And the same thing, and these are say E1 prime, B1 prime, and E2 prime, B2 prime in frame B. Is this clear? So this is what we have. How are these two going to be related? Then E prime of U, I'm taking the particular place of alpha and beta, which we looked earlier as 1. Okay, for simply, you could put alpha in. What should this be equal to? Anybody?
So negative of QV cross B dash.
No, nothing like that. No, I don't need anything. It's just, we know what it, see, what we have told is it's E, if you see E1, B1 in frame A, and then you will see E1 prime, B1 prime in frame B. If you turn on E2, B2, then that will become E2 prime. So all I want is something which is even simpler than that. The frame is not being changed. So I want that this formula here, so what we are looking for is a formula of this kind where E and B could be anything. These are just placeholders. You can put any value. So I'm just changing it to that. So E prime of U, E2, B2. Do you agree with this? This is what I mean. Similarly for B.
So what is this normal E prime in relation to E1 prime dash and E2 prime dash?
We don't know that. We don't know this formula. We don't know we are going to derive a formula for this.
No, sir, the E1 prime dash and E2 prime dash that you had defined
Yeah,
later.
yeah. So what I'm saying is, suppose we observer A was in some, so these two observers exist. They can turn on sources. They can do various things. Okay. So observer A turns on something, creates some sources, and measures electric field E1 and magnetic field B1. Okay. Then observer B will measure the same. It's the same setup. Observer will measure E1 prime, B1 prime. That's what I mean. For the same setup, same sources, same everything.
Okay, sir.
Similarly, now if observer A tunes something and will get some different electric field, E2 and B2. Say I'm just saying that observer B will see E2 prime, B2 prime. So this goes with this, and this goes with this. That's all I'm saying. But now what I'm saying is that, like in superposition, observer A can create something where the electric field is E1 plus E2, and magnetic field is B1 plus B2. Then linearity on both sides, like, okay, so linearity will force this. You think a little bit. That's what it would say. Okay, so this is what we would have called. This is what we would have called. We would have called this E1 prime, and this is E2 prime.
Oh, that is what I was asking. Yeah.
Okay. Sorry, I jumped one step. So, right. So because that formula is one formula, so where you just have to change its arguments. Similarly for B. Okay, so this is it. So now, so these are the constraints that we have, and this is strong. This is okay. So the claim is that these constraints are strong. So now let's come back to our experiment. Okay, and what I want to write is that okay, so one thing we saw, yeah, so let me just write some formula and then we will see. Then E prime should be, okay, should I be, let me actually not, let's not go back to our experiment and then write something. Okay, now let me just explain why I wrote something like this. Okay, so first thing is linearity means in this general formula, this linearity actually says that whatever we write here in this, where is this? I haven't got overshot it here. So in this guy, the E and B should come only to linear order. You need not be linear. There's no linearity involving you. U is just going for the right. So I'm now expanded as a power series. We know at U equal to 0, E prime equal to this. So I'm asking what is the first correction. I'm writing these things. But now so I need to create vectors. Given two vectors U and B, I can create U cross B. I could create U cross E. Okay. But now I want to explain why I wrote that E prime gets U cross B. Why is that? B is axial. U is a polar vector. It's a velocity. So U cross B is, what is U cross B? It's a polar vector. So it can only appear as a correction to E prime. It cannot appear as a correction to. Is this clear? This is a polar vector and this is axial now. cross product of two polar vectors is an axial vector, so it can be added. Is this clear? So these are the only terms. So I'll just stop here. To order U, these are the only possible terms compatible with the properties. That I just mentioned. Okay, so what are the properties? It said if you switch off U, it goes off. So we are asking when you turn on U, I'm just writing something like this. So we get A1 and A2. These are just some constants which we have to fix. Okay, we will do that in a moment. But all I'm saying is that this is the only terms which I can write. I cannot write any more. Okay, so next lecture, which is tomorrow, no, day after, we'll work out what these constants are. Okay, so we'll work out everything to order U and then ask what does that mean. Okay, so I'll stop here and pause for questions or comments, anything. Okay, so
Sir, how did we write these expressions? E
yeah.
dash